All right, good afternoon, everyone. Can you do me a favor and open up your unit handout to page 17 where you had a few problems to do from yesterday? I want to not only review what we learned yesterday, but add some details to it that I didn't feel the need to go into yesterday. So the first one is, we call this the Bohr atomic model. And even though Bohr is only able to come up with energy level values for hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, the underlying idea of what's going on in the atom is true regardless of the atom. So when you look at a calcium atom, there are energy levels. When you look at a uranium atom, there are energy levels. So the nucleus that I have down here is not hydrogen, obviously, because hydrogen's nucleus has one proton, and later on in the unit we will learn that some hydrogen nuclei have a proton and a neutron, or a proton and two neutrons. There are different varieties of hydrogen. But this can be any nucleus, and every atom has a ground state, and every atom has an ionization state. And this series of three dots near the top of the diagram, the energy level diagram, is telling you that mathematically and in principle, there are an infinite number of energy levels. They get closer and closer and closer to each other. No matter the atom, they get closer and closer to each other as you go further out. But when you look at the hydrogen energy level diagram that I gave you yesterday, that you probably have in front of you, there's a nice sequence in terms of the spacing of the energies, that from E1 to E2 is quite a large chunk of energy, and then 2 to 3 is less, and 3 to 4 is less, and it just keeps getting smaller and smaller and smaller. There's no rhyme nor reason to what happens with anything outside of group 1A. All those hydrogen, lithium, potassium, rubidium, cesium, whichever ones I can't remember, they all follow that same pattern. But the mathematics to explain something like helium, which just has two protons in the nucleus, escalates out of control. It's absolutely out of control. I have a degree in physics. The most complicated atom we studied in my degree was hydrogen. And when you actually study it in detail, it's complicated. So as soon as you add more electrons and more protons and more neutrons, it gets out of control. But if I asked you right now, what does Dalton say an atom looks like? You can say it looks like a billiard ball. What does Thomson claim an atom looks like? It looks like a plum pudding. He was British, so that was what he used. What would Rutherford say an atom looks like? It looks like a solar system. It looks like planets orbiting a star. Bohr is not saying an atom looks like this. We're stepping away now from talking about what atoms look like, because maybe it's not important what it looks like. What's important is how it behaves. Often we will draw a nucleus, and these energy levels we draw as concentric circles. And you'll often see the label on there, Rutherford-Bohr model, which means it's the Bohr model. It has those energy states that are quantized, but the electrons are in circular orbits. And for the time being, we can buy that. But the bottom line is, this is not a picture of what an atom looks like. The most important aspect is, if an electron jumps to a higher state, it has to take in an amount of energy exactly equal to how much energy it gains. I mean, that sounds like I'm just repeating myself. But to go from one energy level to a higher energy level requires a discrete, fixed amount of energy. And that's the energy the electron gains, so that's the energy it has to absorb. If an electron, quote, jumps to a lower level, then it's going to lose a very specific amount of energy. In either case, this will change slightly today. In either case, that energy is accounted for by a photon. And when I say accounted for, it's like accounting. When you do accounting, you're finding where every penny goes. There's an accounting of things. Here, there's an accounting of energy. If the electron jumps to a higher level, it will absorb a photon. If an electron jumps to a lower level, it will emit a photon. This statement here is not always true. There are other ways to get an electron to move up. The statement below it is always true. If an electron falls to a lower level or jumps to a lower level, it will emit a photon. And the most important thing is this fourth statement. The energy is conserved. So, I don't know why I hit my laser and expected it to go forward. So this is what you're using to find wavelengths. You're taking a change in energy of the electron based on the energy level diagram, and you're setting that equal to the change in energy of the electron is set equal to the energy of the photon. And there's something else I want to talk about, but I'm just going to, it's this bottom pair of statements. I'm going to leave that alone for now. So here is a typical energy level diagram for hydrogen. These numbers are only good for hydrogen. If I asked you about photons emitted or absorbed in helium, you would need a helium energy level diagram. Lithium, you need a lithium energy level diagram. So what I had asked you to do is use this idea along with the energy level diagram of hydrogen that I gave you yesterday. Is there anybody else who needs an energy level diagram for hydrogen? I asked you to fill this in. So what this square in the top right corner is going to be is the wavelength of the photon that's emitted when an electron goes from n equals 7 to n equals 1. So you would take your energy level diagram, and you should have already done this, okay? And you would read E7 is negative 0.278 eV, and you would subtract E1, which is negative 13.6 eV, and then you would take that energy and set it equal to hc over lambda. On the other hand, you could look at the other side of this sheet and take E7, which is 13.322, and subtract E1, which is 0. Okay? I feel the need to tell you, though, if you do all of these subtractions, you might get slightly different differences on one side than the other. And that's just because of rounding. Anyway, when you take that energy level difference and you set it equal to hc over lambda, you end up with a wavelength of what I believe is 93.2 nanometers, which is ultraviolet. And I'm starting here for a reason. 2 to 1. When you did 2 to 1, you should have gotten 122 nanometers, which is ultraviolet. Think about this for a second. Look at this energy level diagram. From 2 to 1, which is that huge, huge jump in hydrogen in terms of energy of the electron, that's already ultraviolet. Anything higher down to 1 is still going to be ultraviolet. It has to be because it's more energy. And I've mentioned this, I think I've mentioned it. The energy transitions in most atoms will never be that great as to produce X-rays. And I say in most atoms because there is something, a type of X-ray production that atoms can be responsible for, but we will not worry about that. So here are the wavelengths for all of the transitions from higher energy levels down to n equals 1, up to 7 to 1. And the important point I want to make is they are all ultraviolet. If I do 7 to 6, and I want you to look at your energy level diagram in front of you. Look at how close the energies of 7 and 6 are together. It's paltry. It means it's minuscule. There's not much there. Well, then you get a super long wavelength, 12,000 nanometers, which is infrared. You will, well, no, I'm not going to say what I was going to say. Okay, you get 12,000 nanometers. If you do from 7 to 5 or 6 to 5, you're going to get infrared again. I would like you, even though it's not on here, I would like you to find the wavelength right now when an electron goes from the ionization state down to 5. And what that means is an electron was just drifting by, minding its own business, and the electron was captured by the atom, and it went all the way down to 5. So you're going to take E infinity minus E5, and then take 1242 divided by that. And I don't have my calculator out here. I don't want to bring it out. I think this is something you should be able to do. Just by my rough estimate, you're going to be getting around 24,000. Help me out. 2283. Sorry, 2283. Is that infrared still? Yeah, it's bigger than 700. So anything down to 5 is going to be infrared. And the reason why I want you to do these calculations is there's an important point here, that anything down to 4 is going to be infrared. 4 is just such a high state that anything above that is not much more above it. And it turns out anything down to 3 is infrared as well. So because of that big gap between 1 and 2, anything down to 1 is a huge amount of energy, which is ultraviolet. Because of the crowding together of the energy levels from 3 up, because they're so close together, they're all infrared. There's a sweet spot that produces some visible light. And it turns out that when you go 3 to 2, you get this number. Now, this does not match the 656 that's in your notes, but that's because we're using an energy level diagram that doesn't have all the decimals. Okay, we don't need to worry about that. And you'll notice it's in red. I've drawn this in red. The V here stands for visible, not violet. It's visible. And when I go 4 to 2, well, guess what? I get that next wavelength in that visible series that we were looking at. And it happens to be green. Then I get 434, which happens to be blue. Then I get 410, 411, which is that color we can't, I don't want to say you can't see the color. You can see the color. But there's not a lot of light coming out of hydrogen, which is important for Monday. What that's telling you is because, I mean, this violet is a difficult color to see anyway, but it's dim. And that means there's not many photons of this wavelength. There's a lot more photons that are red photons coming off. And what that means is, for whatever reason, the electrons in hydrogen do not go from 6 down to 2 nearly as often as they go from 3 to 2. Right? Give me a second, because I was going to make one more point before I reveal that last one. And for the life of me, I can't remember. It will come to me. When you go from 7 to 2, it turns out that that's the tipping point. And from 6 to 2 is still a visible light photon, but from 7 to 2 turns out to be ultraviolet. And 8 to 2 will be ultraviolet, and 9 to 2, and 10 to 2, etc. So that's why there are only 4 visible colors that we see, 4 visible wavelengths. I asked you to complete 1 to 3. Does anybody have any questions from anything we just talked about here up to and including revealing all of these wavelengths, or 2 or 3? Yeah. 3? And I understand why. There's something goofy about 3. And you know what it is? It's because, and I've covered up the answer intentionally, and I don't want you to tell me the answer, okay? It's because if I told you the 2 energy levels in hydrogen, you could find the wavelength by subtracting the energies and setting it equal to hc over lambda. If you knew the bottom energy, but not the top, then you could find the energy of the photon and add it to the bottom to find out where the top is. But we don't know either the top or the bottom. And there's no direct approach here by using a formula. What we need to do is find the energy of this photon, and I guess I need to address something here. This energy level diagram, whether you're looking at the front of this sheet for hydrogen or the back, these are all in EV. Sometimes you're given energy level diagrams in joules. Sometimes you're given it with the negative setup. Sometimes you're given it with the positive setup. You have to be able to use whichever one is given to you. Since we're working here, Charlie, off of the ones that have EVs, we're going to calculate the energy of this photon in electron volts. And you're going to do that using HF. I mean, we use HC over lambda so often, but sometimes HF is the way to go. And I need to take Planck's constant and multiply by that frequency which gives me 12.8 EV. So here's what the challenge is. What two energy levels are 12.8 EV apart? Right, and it becomes puzzle-like in its nature. It's not an equation we can put this number into and get the answer coming out. The first thing you would do, well, the first thing I would do, even if I wasn't familiar with this hydrogen energy level diagram, is when I looked at it, I go, well, wait a minute. From n equals 1 to n equals 2 is a whopping 10.2 EV. And I can figure that out by looking at the side where 0 is at the bottom. And I can see that E2 is at 10.2. Or if I had the other side available to me, I can see that it's a big difference, and I can take negative 3.4 minus negative 13.6 and get 10.2. So this is kind of what I was talking about earlier. This photon, 12.79 whatever EV, is a huge photon energy-wise. It's ultraviolet. So it must be from something down to 1. That's a big start. Because then what I can do is I can take my energy level diagram I got to find one here. I can take my energy level diagram and I can start taking maybe E3 and subtracting E1 and seeing if I get 12.8. This is what you have to do. There's no other way around it. I think it might be 4 to 1. And you understand it's not going to work out perfectly because all numbers given in questions are thought to be the result of some kind of measurement. So there's always some discrepancy to them. It has to be that way because all of these constants have a bunch of decimals and we don't have access to them all. So I think if we take E4, which is negative 0.85 minus negative 13.6, we get close enough to say that that's it. So it must be from the fourth energy level to the first. And I mentioned yesterday, but I'll just mention it again, you're always going upper minus lower. You don't go final minus initial. Way back when I told you delta meant final minus initial, I would have said, there's one exception, and this is it. We don't want to look at a negative change in energy. We just want the bigger minus the smaller. Does that help? Any further questions before we move on today? This is a pretty big deal in this course. Like when you look at your diploma exam, even though it's not necessarily supposed to be this way, there's an awful lot of photoelectric effect and energy level calculations and stuff dealing with photons. So we're going to move on today and look at another series of examples.